Okay, so yesterday in my interaction session, I talked about normal. Okay, and the normal, I didn't say anything about normal to a surface at the beginning, but later on, I think I also explained to you how we are going to find out the normal to a surface at a particular point. But yesterday we were basically talking about the normal at a point to a space curve. Okay, normal at a point to a space curve. So it was something like that. It was something like that. Say, suppose you have a curve like this, and then if this is the tangent, say, suppose this is denoted by RT, if this is the tangent at this point, so then what we do, we are going to find the normal, in this direction. So then I also explained to you why choose only this direction, because what we are going to do, we are going to choose the normal along the direction of the vector t prime, where your t is nothing but the unit tangent vector given by this expression. Okay, of course, we have to assume that r prime t is not equal to the 0 vector. Okay, so I think at that juncture, somebody asked me about the utility of the normal, or what is the physical significance of that normal. Okay, and interestingly, yesterday I have received another query from a student. I think it is Rashmi Bajaj. So she again asked me, if the curvature of a curve is kappa, then why the radius of curvature is 1 by kappa? Okay, so I would like to explain this today. And along with that, you will get to know about another utility of the normal. Okay, another utility of the normal. Okay, and in the process, we are going to discuss about your osculating plan, okay, and osculating plan and osculating circle. Okay, you will see that these concepts, I think I'll be able to finish this lecture within 5 minutes or so. It is not, I'm not going to take too much time of yours. Don't worry about it. Okay, so now let us come to the concept of osculating plan. So what is an osculating plan? So yesterday, while talking about this normal, obviously at the beginning you have to talk about the tangent. Okay, so here you can see this is the tangent. Okay, and as we have seen that, we are going to take a unique direction in order to find out the normal at this point to this curve. So the normal is going to be something like this. This normal is going to be something like this. Okay, so this red pen, it will designate the direction of the normal. Okay, and we know how to find out the direction of the normal in a unique direction, and that is nothing but along the direction of t prime. Okay, and so that means I have this tangent and I have this normal. I have this tangent and I have this normal. Okay, so now consider these two vectors, the tangent vector and the normal vector, independently. Consider these two vectors. So suppose you are visualizing about two vectors. Obviously they have got different directions. Okay, so now obviously these two vectors which have different directions, they can define a plan. So basically we can consider a plan on which the two vectors lies. Okay, and that orientation of that plan is going to be unique. Okay, and that is going to be determined by the tangent and normal vectors. So if you consider that particular plan, it is called the osculating plane. Okay, the plane on which the tangent and normal to a curve lies, it is called the osculating plane of the curve at that particular point. Okay, fine. So far so good, right? So now the question is again, question from Rashmi was why the radius of curvature is always 1 by kappa, where kappa is the the curvature of a curve. Okay, I'll answer to that. But before that, I'll have to do some more, not really computation. I'm going to talk about something more here. Okay. So now I don't want to go back to the definition of curvature, all this stuff. So basically, you know that curvature, I think kappa, it was defined as mod of t prime t and mod of r prime t. You know what is what here. Okay. So now, there is an example worked out in Stewart book, and you can easily find it out. And of course, I'm going to do that particular exercise, which is at the extreme right. So, if I consider a circle, of radius a, if you want to find out the curvature using that formula, you will always find out that kappa is equal to 1 by a. Kappa is equal to 1 by a. So that means in order to define a circle, or in order to determine a circle, if you can find out the curvature, you can easily find out its radius. Say, suppose the radius is not known, but by some way you are able to find out the curvature. Okay? Since this is always valid for a circle, so from that curvature, we can always find out the radius to be 1 by kappa. So remember, this is for a circle, because we know that it is already a circle, that is why it has a radius, right? And the radius, the curvature is known, we can find it out simply by taking its reciprocal. Okay? This is not a general concept. This is only for that particular circle. Okay? So now let me come back to the osculating plane. Let me come back to that osculating plane. Okay? See, again, remember, whenever we are considering the osculating plane, it is not necessary that the original curve C on which you were considering the tangent and the normal, it is going to lie on that plane. It is not necessary, because if you consider a space curve, it is highly unlikely in most times, right? If space curve, it is highly unlikely that it is going to lie on a plane. Only when you are considering a surface to be a plane, then something like that may happen. Okay, but generally it is not going to lie on a plane because it is a space curve, right? So that is why the location of the point on which we are considering the tangent and the normal, it becomes important. Okay, fine. So now think about this. Now you think about the osculating plane. You think about the osculating plane. Okay, so now suppose this is my curve, something like this. Suppose my curve is something like this, or maybe let me something like this. Okay, and remember, although I have drawn it in the plane of this blackboard, it doesn't exactly lie on the plane of this blackboard. Okay, fine. So it is something like this. You see this. You see this. If you consider this as a curve, you see this. It doesn't lie on a plane. But at this particular point, say this tip of the finger, you should please look at this. At this particular point, if I consider the tangent and normal, that is going to define an osculating plane. And you please think that this blackboard is the osculating plane. Okay. So then suppose at this point I am considering the tangent and normal, and obviously you will see that the tangent is always going to be drawn at a place where the concave side is going to be below the tangent line. Okay, fine. So now in that osculating plane, so suppose this is the osculating plane, this is the osculating plane. Okay, and because the tangent and the normal lies here, tangent and normal lies here. So now at this particular point, let me compute the curvature of this curve. Suppose this is kappa t. So then now if I want to consider a circle on that osculating plane passing through that particular point, okay, with its center towards the, inward direction of that normal, okay. So then from the original circle we already know that for a circle, if I can find out the curvature, then the radius of the circle is simply what? The reciprocal of the curvature, right? So by considering a radius A, what I can do, I can draw a circle like this. Where this radius is going to be given by 1 by kappa. Okay, so that is why when the curvature is kappa, the radius of curvature is 1 by kappa. Is it okay with everybody? Fine. And again, you shouldn't think that this circle is going to be small. This circle is always going to be included inside this portion. Okay, it is not necessarily so. So depending upon the curve under consideration, this circle may be something like this also. Okay, fine. And this circle is called the osculating circle. Okay, so now you know that in fact the origin of the way the radius of curvature is defined, in fact it has come from the concept of that osculating circle, and for that matter osculating plane. So yesterday whoever asked me about the physical interpretation of the normal or its utility, this is another utility. Okay, so I hope the concept is clear to you now. Fine. How the term radius of curvature, it has come into the fore. Okay, so now let us try to work out this example, so then it will be more clear to you what I was talking about. Okay, so this is about find the equations of the osculating circles of the ellipse 9x squared plus 4y squared equals 36 at the points 2, 0, 0, 3. Okay, and always remember, I have formula for curvature. I have formula for curvature in Cartesian code. So the example is 9x squared plus 4y squared equals 36, and you can convert it into x by 2 whole squared plus y by 3 whole squared. This is equal to 1. Okay. So now if you parameterize it, our job becomes much easier. So if you parameterize it, then this ellipse can be parameterized by this vector. This is going to be 2 cos t, 3 sin t, and because it is a space curve, you may add the third component as 0. Okay, so then this is equal to minus 2 sin t, 3 cos t, 0, and r double prime t this is equal to your minus 2 cos t, then minus 3 sin t, 0. Okay, so now you know that, I mean, in terms of the vector RT, the radius of, not radius of curvature, sorry, the curvature is given by this formula. I think it was R prime t whole cube. I hope I'm correct. Yes, I hope I'm correct here. Okay, so now if I want to find out your r prime t cross r double prime t, so then you can see that this will be simply I j k and then minus 2 sin t, 3 cos t, 0, minus 2 cos t, minus 3 sin t, 0. Okay, let it be like this something. Okay, so now one thing here. So here we have been told to find out the equations of the osculating circles at the points 2, 0 and 0, 3. Okay, now if you look carefully here, if you plug in these two components there, so then you will see that if you plug in 2 cos t equal to 2 and 3 sin t equal to 0, so then you are going to get cos t equal to 1, right? So that means this corresponds to your t equal to 0, and similarly, pretty easily you will be able to find out that this corresponds to t equal to pi by 2. This corresponds to t equal to pi by 2. Okay, so now, and that means, I mean, if I want to find out the cross product corresponding to t equal to 0, so that is going to give me what? Your this r prime t, r double prime t, I mean corresponding to t equal to 0. So this is going to be, I'm just going to find it only once. So this is going to be 0, 3 and minus 2, 0, 0, 0. So obviously here you can see that your both I and j component, it is going to give you 0. Okay, and for the k component, it is going to give you 6k. 6k. Okay, so basically if you take the mode of this, that is going to simply give you 6. And I can guarantee you that if you want to find out corresponding to t equal to pi by 2 also, I mean, even though the components are going to change, like say, then this is going to be minus 2, this is 0, 0 minus 3, and from there also, only 2 and 3 remains here. So 2, 3 are 6, whether it is positive or negative. Eventually, the mod of this is again going to come as 6. Okay, so this part, irrespective of whether t equal to 0 or pi by 2, it is always going to give you 6. Okay, so now let me try to find these two out. Okay, so so that means for the point 20, which corresponds to, I mean, t equal to 0, so this is 6, and then your r prime t, I can find it from here. So corresponding to your t equal to 0, mod of r prime t is simply going to give you 3. Is it okay? Fine. So it is 3 cube. So that means it is 2 by 9. Okay. And similarly for 0, 3, your k pi by 2, obviously the numerator is 6, and in the denominator, what you are going to get again from here. Pi by 2 is going to give you this as -2. So if you take mod, so that is going to give you 2. So this is 2 cubed. So 6 by 8. So that is 3 by 4. 3 by 4. Okay. So we have got the curvature. So if I want to draw the osculating circle at the point, I mean 2, 0, so then what must happen? What must happen? The radius of curvature, say if I call it A, it is going to be your 9 by 2. Similarly, here, radius of curvature is going to be 4 by 3. 4 by 3. Okay, fine. Just let me close the door so that close the window so that the lighting is okay. Fine. So now let me try to draw it, how it is going to look like. Okay. So this is your ellipse, which has semi-major axis. I have found out x by 2, right? So 2 and semi major axis is going to be 3 and minor axis is going to be 2, or do you call it, if it is along x and y, x it is called major, y it is called minor. It is not necessarily so. So basically I have all the information here. Okay, see, suppose this is 1, this is 2, this is 1, 2, 3, 1, 2, 1, 2, 3. So it is going to look something like this. Okay. So this is 1 point, 20. This is 1.03, where we have to find out the osculating circles. So now, if you look at this, point, so what is being given? Like the radius of curvature is 9 by 2. So that means it is 4.5, right? It is 4.5. So then what must happen? 4.5. So this is 2. This is 4. So you have to come half here. So this is going to be your radius. So then what you have to do, you have to draw a circle like this. That is going to be the osculating circle corresponding to the point 2, 0. And you know that, like say, this is 0, this is -2. So this point must be minus 2.5. So minus 2.5 is minus 5 by 2. So the osculating circle is going to be your x plus 5 by 2 whole square plus y minus 0 whole square, that is y square, and that is equal to your 9 by 2 whole square. Okay, this is for the point 20, right? Now if I come to is it 3 by 4? No, I made a mistake here. Sorry, it is not 3 by 4. But I made a mistake here because it is going to be 6 by 8, right? 6 by 8. Okay. 4 by 3. Okay, so it is going to be your so it is fine. A is 4 by 3. Okay, so now let me concentrate on this point here. So this length was 3. So and you have to find out the circle which radius 4 by 3, right? So like the y coordinate of the center is going to correspond to 3 minus 4 by 3. So it is going to be 5 by 3, right? 3, 3, 9. Yeah, 5 by 3. Okay. So the osculating circle corresponding to this point, it is going to have center at 5 by 3, 5 by 3. So somewhere here, and you are going to get something like this. So basically, it is going to be x squared plus y minus 5 by 3 whole square, and that is going to be equal to 4 by 3 whole square. Am I correct? Yeah. I think, yes, I think that's it. So I hope the concept of now the radius of curvature, where the origin of that terminology come from, and osculating circle as well as osculating plane is clear to you now. Okay, thank you.